main purpose of study of our paper back in 2018. And actually, there are recent experimental progresses in demonstrating these topological effects in Moire systems. So my talk will be divided into two parts. Basically, unfortunately they're not that related, but they are both about Hofstadter butterfly, and actually, yeah, there are some connections in the topological aspects. So in part one, I'm going to talk about the method which we call the open momentum space method for Hofstadter butterfly. This actually provides us some new understanding of the duality between real space and momentum space in Hofstadter butterfly. And in part two, I will focus on the effect of the band topology on Hofstadter butterfly, which actually can be tested experimentally. Okay. So I assume most of you are familiar with the concept of Hofstadter butterfly. It's basically the energy spectrum of electrons in two-dimensional periodic lattice under magnetic field B. So in general, this requires to see the Hofstadter butterfly. This requires the magnetic field B to be actually very strong, so that the flux per unit cell is comparable to the flux quanta divided by 2 pi h bar over E, which I'll just call 2 pi later. So, so for normal lattices, this actually requires the magnetic field of the order of the magnetic field of the neutron star. So it's not that easy to realize. But theoretically, it's a very interesting topic, actually, as first shown by Hofstadter in 1976. He studied the spectrum of the square lattice tide binding model in magnetic field B. And he found this interesting fractal behavior of the spectrum. Basically, the spectrum is periodic as phi goes from 0 to 1 units of phi naught. The other thing to notice that is at a small magnetic field B, one has these Landau levels, which are expected basically from the QRP model perspective, while at large fields, these Landau levels expand into bands, and actually you can see the Landau levels from bottom and top merge together at the Van Hoff singularity of the band structure, which merge into this kind of fractal behavior. So the conventional method for calculating the Hofstadter butterfly assumes the periodic boundary condition. And this is only possible if you require the magnetic flux per unit cell to be rational. By rational here, I mean the magnetic flux per unit cell is 2 pi times P over Q, where P and Q are integers. Here, I assume they are coprime integers. So as a result, you find if you combine Q times of the original unit cell into a magnetic unit cell, the system still has a translational symmetry. This is basically because, for example, for phi equal to 2 pi over 3, so Q unit cell together encloses a flux of 2 pi times P, which is two integer multiples of 2 pi. And this actually recovers the translational symmetry, and one could calculate the spectrum just as usually what we do for the block bands. But because the unit cell becomes Q numbers larger, the number of bands in such a calculation actually increases by a factor of Q. So for example, in Q plus 3 case, if originally one has one band, one would the band would be divided into 3 subbands at phi to 2 pi over 3. As a result, this gives us these rather discontinuous behavior of this spectrum. Basically, at each different rational numbers, the number of bands are different. So yet there's another actually widely used method for calculating the spectrum in magnetic field, basically the Landau levels of QRP model. So basically, if we have a cutoff P model of solid expanded, for example, at a position K naught, so basically this is a such kind of models are obtained by expanding the band structure near a certain momentum K naught in power of K minus K naught. So such models would resemble electrons in the free space with a particular kind of kinetic energy. For example, in graphene, one has Dirac electrons near K and K prime points of the system, which just behave as the Dirac fermions we usually study in high energy physics. So the method for calculating the Landau levels of these cutoff P models is just to replace these quasi-momentum by the Landau level raising and lowering operators. Basically what we do is to regard this quasi-momentum as a realistic momentum, as the actual momentum. So we can just define the Landau level operators, and these Landau level operators would basically be a matrix in the basis of a Landau level basis, and by just replacing these Ks by these matrices, one would obtain these Landau levels of the cutoff P model. So in actual calculations, what we usually do is to put a Landau level cutoff. Basically, the Landau level number has an upper bound in L, which is up to choice. So basically, the method we proposed is we propose this method actually also applies for calculating Hofstadter butterfly. Basically, if we write any lattice model in a quasi-momentum space, and replace those quasi-momentum by these Landau level raising operators, with the A specifically being a matrix like this, and you add a Landau level cutoff to it, you would obtain the Hofstadter butterfly spectrum. This is actually not that straightforward to understand, because these Ks are actually quasi-momentum instead of a realistic momentum. So one might wonder why that would work, but actually indeed it works, and I'll explain basically in the rest of the talk why. So this is an example we calculated for a square lattice type Biao model. So the momentum space Hamiltonian for such a model would just be minus cosine kx minus cosine ky. Here I assume the hopping is 1/2. So basically what we do is just to replace these kx and ky by the matrix here, and calculate the cosine of this matrix. And basically note that this L here, I forgot to mention probably, is the magnetic lens, which has a magnetic field dependence. So by changing the magnetic field, basically this L changes, and one could obtain such a spectrum as shown here. So interesting thing here is, for this calculation, actually you don't need to assume the magnetic flux to be a rational number. It can be any number, you just change it continuously. But as you can see, it indeed gives you the outline of the Hofstadter butterfly. And actually, as the cutoff is bigger, this Hofstadter butterfly spectrum becomes more precise. So, but this is still different from the Euro calculation. You might have already noticed that in the Hofstadter gaps, there are many flowing levels, which we call the spectral flows. So so why would this calculation have these in-gap spectral flows? So it turns out that these spectral flows in the Hofstadter gap can be understood as the momentum space edge state. So this is so later I'll provide a more concrete understanding of what the momentum space this means, but here we could understand this actually just from a rough picture. Basically, what we did here is to replace the quasi-momentum by these Landau level operators. So if you calculate the norm of these quasi-momentum centered at K naught, you find K minus K naught is basically bounded by this cutoff. So this is assuming, for example, the quasi-particle extends all the way outside the first Bernoulli zone. So this is a momentum space lattice. Then you would find the basically your quasi-momentum in this bigger space can only cannot exceed this radius proportional to square root n L. So this actually gave you so if you regard the model as a momentum space model in this reciprocal lattice, actually you find these in-gap states can be understood as the edge states in this momentum space. So this can be more clearly seen by looking at the wave functions of these edge states, in-gap edge states. So this is a typical example. Basically, it's a state about at the position here. So basically, you can see as a function of the Landau level number, basically the wave functions plotted. If you plot the norm with respect to the Landau level number, you find for edge state, the wave function is mainly concentrated near the cutoff NL, cutoff Landau level number. Here it's taken as 500. So basically, because square root NL is basically the radius in momentum space, you could identify this as an edge state. So in contrast, if you take a bulk state, a typical wave function would look like this. You see the wave function is almost uniformly distributed in the all the Landau numbers. So basically, by identifying the weight of the wave function near the edge, one could actually identify these edge states and delete them in the numerical calculations. And this is a result after we delete these edge states by some edge projector, and you find a very clear Hofstadter spectrum. But I want to notice that actually this spectrum is not ideally symmetric about 0 and 1. Basically, the cutoff actually breaks this symmetry between 0 and 1. Okay, so the method actually also applies for to the other kind of another large class of models, which we call the continuum models or the plane wave expansion models. And this is actually the first place we apply this method. We applied it to the twist graphene continuum model. Basically, this kind of models are just derived from another perspective. Basically, you start from the electron kinetic energy in the free space and add a lattice potential to the system, but expanded in Fourier components. Basically, these QJs are the Fourier momentum of the periodic lattice potential. So they basically take the integer multiples of the reciprocal vectors. Yeah, such models are used to actually describe the Moire systems where the kinetic energy comes from the microscopic lattice, and the Moire lattice provides the additional potential, periodic potential. So by Fourier transforming this model into the momentum space, one would obtain similarly a momentum space Hamiltonian, which actually contains a kinetic term expanded at every reciprocal lattice vector Q. And there's a hopping among different lattice potentials connected by these Fourier components Qj. So for example, this is the lattice for twist-body graphene, if you're familiar with that. Yeah. So basically, in this model, one has a kinetic term on each of these momentum sites, and there's a hopping connecting these different momentum sites. So to calculate the Hofstadter butterfly of this such a model, one could similarly just replace the K here. It's also quasi-momentum. Replace the quasi-momentum by these Landau level operators, lower raising operators, and you can choose any K0 actually to expand the quasi-momentum. The result doesn't quite depend on K0. So the difference is now one actually requires two cutoffs. One is the cutoff in the Landau level number. Basically, I call it NL. And the other cutoff is the reciprocal lattice cutoff. Basically, in general, the lattice is actually infinite lattice, but for practical calculations, band structure calculations, one always need to take a reciprocal lattice cutoff NQ, basically the number of Brillouin zones enclosed in this model. So this is an example of the two-spot graphene model calculated with NQ equals 36 and L equals 60. And indeed, one also see these Landau level, these Hofstadter spectra emerging, and also these in-gap spectral flows. So similarly, one could actually also identify these spectral flows as edge states in momentum space, and one could delete them. After deleting them, actually, one can get a clear box spectrum. Here, the spectrum is not that clear because basically the cutoff number is still not big enough. So basically, what happens is these two cutoffs give us the momentum space boundaries. So basically, the reciprocal lattice cutoff gives us a boundary. For example, I just cut it off here, while the Landau level cutoff also gave us a radius cutoff. And basically, the smaller one of these two boundaries plays the role of a momentum space boundary, and that's where these edge states are located in the momentum space. Okay, so yeah, just now I just talked about some rough understanding of the model, but actually it's still not quite clear why that method would work. So to understand why the method would work, we actually identify the basis for for the calculation of such Hofstadter butterfly. So let me first talk about continuum models. So basically, for continuum models, the two operators one could use to define the basis are the kinematic momentum, which is just the kinetic momentum minus the gauge potential, A. And the other quantity is the guiding center. Guiding center, basically, semi-classically, it's basically the electron is doing circular orbitals on a magnetic field, and the center of this radius, the center of this circle is basically defined as guiding center. Basically, these two operators commute with each other, so one could use them as the quantum numbers for the quantum numbers of the eigenstate, eigenbasis one use. So for previous Hofstadter method, for example, the model of two-spot graphene is studied by Bistritzer and McDonald in this PRB paper, where they calculated the Hofstadter butterfly of the system. So there, they basically the basis they choose is basically the eigenstates of the Rx operator, the X guiding center, and the pi squared, basically the kinetic energy, kinetic momentum squared. And this is basically proportional to the Landau level number, A. So the pro of this calculation is actually one could take a Landau level cutoff in this method, and the model is still translationally invariant with this Landau level cutoff. So one could then apply the block theorem to calculate the Hofstadter spectrum. However, the matrix is actually a dense, complicated matrix, which is very difficult to implement if you try to do the calculation. It involves the special functions carefully, calculating the matrix elements using special functions. And the matrix is dense, which actually costs a lot of computation power. So what we find is for the open space method we just mentioned, the basis actually involves 4 quantum numbers. So still, one would use basically the kinetic momentum and the guiding center to define the basis, but in a slightly different way. So basically, for we choose the guiding center along a certain direction to be one of the quantum number, but we need to divide the eigenvalue of this R tau operator, which is a real number, into two parts. Basically into a number lambda, which I'll specify later, and a number basically given by the reciprocal size q. And for each reciprocal size q, we can define a lambda level basis by using a q-dependent lambda level operator in the Euro way. Basically, A is equal to n, but this AQ is actually a shifted lambda level operator. Basically, it's shifted by the constant qx and qy at the momentum sites q. So basically, different AQs are not independent, but this is basically how we define the basis. For each q, we need to use a different a to define the basis. Yeah, this is a kind of weird basis, but the good thing about this basis is actually the matrix elements under this basis becomes very simple. Basically, recall that the lattice potential of the continuum model is takes such Fourier components e to the iq, and actually under this new basis, e to the iq dot r applied on this basis is actually just to give you a shift of q, a reciprocal side by this vector q. But the cone of this method is the translational symmetry would be broken if we take a cutoff along the level or this q lattices, which is the momentum space boundary we actually specify later, just earlier. So just to give some more understanding of this this basis, actually, in order to prove that this is a complete basis, one need to choose the direction in the irrational direction. Basically, if G1 and G2 are the reciprocal vectors of the model, one need to specify that this number is irrational. Yeah, this is actually just because for fixed lambda, your R tau eigenvalues actually take all the values given by all kinds of q's. Yeah, actually, if there are two eigenvalues differing by some expression given by here, given by certain reciprocal side q, the two lambdas should be identified. And in order to avoid a over complete basis, one need to assume that this number is irrational. And as a result, this lambda actually also is in a set of the coset of a real number modified by basically this set given by all the momentum sides. So basically, lambda labels the cosets instead of just a simple real number. Yeah, but this complication is actually worthwhile for the calculations here. So first thing is that this basically defines the completeness of the basis. And the second nice thing about this basis is that the Hamiltonian, one could find that the Hamiltonian is actually diagonal in this lambda basis. So yeah, basically one only need to calculate the spectrum for just one lambda sector. While the other thing, good thing is actually the matrix elements of this H lambda, one could show is just given by the zero magnetic field momentum space Hamiltonian with this substitution that you replace the quasi-momentum by these lambda level lowering raising operators. Basically here these A's are the AQs we just defined, but in matrix form they are all the same. They just take the form of this lowering operator matrix. And the nice thing is that this matrix, all these matrix elements are actually independent of lambda. So basically, although this lambda is a weird thing to define, the result is that you don't need to care about this lambda. All your calculation is just independent of lambda. So just to understand better the basis for in each lambda sector, basically assume this is a tau direction. So basically, the wave functions are located at a fixed R tau for each basis, But basically the center of these wave functions depend on where you choose the Q. So basically, if this is the rotated lattice Z times Q, we find the basis in a fixed lambda sector actually passes through all these rotated sides. So as you can see, there's no translational symmetry unless you take infinite number of them. Yeah, so this is how basically you can think of the wave function look like in the real space. So similarly, we could prove the basis for type binding models. So for type binding models, basically the model in magnetic field are given by the power substitution, where the hoppings are replaced by the gauge phase given by, multiplied by gauge phase given by the gauge field from side I to J. I just want to mention that this power substitution actually only becomes exact in the zero size limit of the Wannier wave functions. But here we don't need that assumption. This is just the original proof of the power substitution. So for the basis of the open momentum space method for a type binding model, the basis can be defined by embedding the model in the real space, in the continuum space. So in the continuum space, if we assume the Wannier orbitals are centered at the position d plus u alpha, which is the starting point of these power substitutions, and d here denotes the lattice vectors. And if we use this d plus u alpha to denote the position eigenstate at r equal to d plus u alpha, so this is a different state than d alpha. It's basically the infinite small delta function at d plus u alpha. Then we can define a basis as basically the projection of the basis we just defined actually here, but by taking q equal to 0, we project them by these delta functions into the Wannier basis. And similarly, this lambda is also required to taking values in this coset. Then we find the similar solution, result that the Hamiltonian is diagonal in lambda, and the matrix elements are independent of this quantum number lambda. And the matrix elements are just given by just replacing this HK and momentum space Hamiltonian by the substitution that quasi-momentum, just into these A's. And one could choose actually any K naught, which actually does not quite affect the spectrum at large magnetic field. Okay,
Hi, I have a comment.
Yeah, sure.
So this, there's been follow-up work since Lottinger's work, and this power substitution has been proven beyond this restrictive assumption. Yeah, that's just a comment. I mean,
I see. Okay, thanks a lot. Yeah, just another comment is that actually our proof here is actually independent of the Wannier function size. So just it's pretty general. Okay. Now let me talk about the origin of the spectral flow. In a more detailed way. Basically, the spectral flow would always occur in a magnetic field when there's an open boundary. So this can be understood from the Strata formula or the Diophantine equation. There are actually multiple equivalent names for such an equation. Basically, the Strata formula tells us that if we look at a Hofstadter gap, the fitting, basically, if rho is the number of bulk states occupied, number of bulk electrons occupied in this gap per unit cell, and T is the Chern number of the gap, then basically they satisfy this equation, that rho is given by some integer plus this Chern number times phi over 2 pi. So actually the Chern, basically the integer can be understood as the fitting of the system of the gap in zero magnetic field, while this phi over 2 pi, is just magnetic field. So basically this contribution can be understood as the Landau level degeneracy contribution, which is proportional to magnetic field B. And this is actually very general, even not for Landau levels. So it's actually a general function, general equation for Hofstadter, any Hofstadter gap. People already studied such a spectral flow in real space. Actually, if you take an open boundary for such a real space, for lattice model in real space, one note that basically this is the spectrum they calculated in such a open boundary system, and indeed one would see these spectral flows as well in the gap. To understand these spectral weight is just to note that this density rho keeps changing as you change the magnetic field B. So, but actually in the bulk there is a gap. So the way that the number of states can change is by flowing the edge state levels into the bulk. So this basically creates the flowing edge state as a function of magnetic field B. And one can actually calculate the spectral flow rate, which is actually proportional to the area, the real space area of the system. So similarly, in open momentum space method here, as we actually already commented, there's actually a momentum space, open boundary due to the cutoff NQ and NL. So as a result, actually, what controls the spectral flow is the momentum space dual of the spectral of the strata formula. This is completely equivalent to the previous strata formula or Diophantine equation. It's just that you multiply both hand side by 2 pi over phi, then you find basically a dual form that effectively 2 pi over phi play the role of phi over 2 pi in the previous calculation, previous equation. And here one could define a momentum space density, basically understood as number of states per reciprocal lattice unit cell. It's related to rho by 2 pi rho over phi. And one could prove that actually this rho k is the number of electron states occupied in each lambda sector, fixed lambda sector. That's basically what we calculate in the open space momentum space, open momentum space method. So again, this so basically in a fixed lambda sector, then rho k times the momentum space area would give you the number of states occupied below a certain gap. So then there are actually two different regimes. In the large B regime, large B field regime, actually, as you can see, this boundary given by the Landau level cutoff would be larger than the momentum space reciprocal lattice cutoff. So the lattice boundary, momentum space lattice boundary is given by NQ, the cutoff NQ. So in this case, the boundary actually is it does not depend on magnetic field B, and one could show that the spectral flow rate is controlled by this NQ, basically proportional to the area of the momentum space, and the coefficient is this S nu. So basically, S nu plays the role of a kind of a dual Chern number in this momentum space. Here is some here in the example here, actually these levels are the spectral flow levels controlled by this formula. I just want to mention there are actually also these horizontal lines, as you can see. This is actually specific for the Dirac models because this is a twist-body graphene model, which contains the free electron kinetic energy as the Dirac fermions. And for Dirac fermions, they actually contribute additional spurious Dirac zero mode due to the Landau level cutoff. Basically, this state becomes a zero energy state of the kinetic energy under the cutoff. And these states actually should be deleted when you count the number of flows. Okay, the other regime of the flow is when you go to the small B field regime. In this case, the boundary is always given by the Landau level cutoff, and it's actually a B-dependent area. The area is B-dependent. oh, sorry, here should be a small, yes, smaller sign. So the momentum space boundary in this case gives us a spectral flow actually proportion to the other integer, t nu, basically the Chern number of the system, and controlled by this NL. So here, and the reason that it's controlled by t nu is because the boundary is also keep changing. The boundary size also keeping changing. So this actually changes the coefficient into t nu. So interestingly, basically by this method, by looking at these spectral flows as small field and large field, one could determine the integers t nu and s nu, the quantum numbers of the gaps. This is basically how we get the quantum numbers in these in this method. So for tight binding models, actually there's no NQ cutoff, and one could equivalent regard it as NQ goes to infinity. So for tight binding models, basically the system is always in the small b field regime, and the boundary is always given by this Landau level cutoff, and always satisfy this spectral flow formula. Okay, so another interesting thing I want to mention is this S nu actually, as we showed, it looks like pretty nicely due to the Chern number of the in the Euro sense. So in some sense, it can be understood as a dual Chern number in the momentum space. And accordingly, because it is well known that the Chern number has topological response, which is the quantum Hall effect. It gives us a integer quantum, quantized integer sigma xy, the Hall coefficient, the Hall resistance, Hall conductance, sorry, proportion to T nu. So one might wonder whether S nu also has a quantized topological response. And indeed, what we find is for this dual Chern number, it corresponds to a quantized Lorentz susceptibility. And basically, one might note that this Chern number T nu, in the response of Chern number T nu, sigma xy is given by the correlation functions between the current operators, basically the current operator jx and jy. So to find the dual of this effect, basically we need to find out what is due to this current operator. It turns out it's the force operator that is due to a current operator, because the current operator is the basically a pumping of the momentum, is partial h partial k. So if one replace the momentum by a real space coordinate, one finds the corresponding quantity is partial h partial x, which is the force operator. And accordingly, the response would be in response to time changing position, which is basically velocity. So basically the response would be a force in response to a movement of the lattice. And this can be also calculated by this correlator, basically the force correlator. And one can show that this coefficient is actually E times B times this integer S nu. So it's also quantized the response. This response actually has an easier understanding, just from the perspective of the semi-classical physics. So just consider a lattice that is moving at a velocity vy in a magnetic field B. So in a moving frame, actually the electron field, there will be an electric field created by the according to the special relativity. If the system is moving in y direction, one would produce an electric field in the x direction, which is equal to Vy times B. So if we examine the current in the rest frame of the system, first, all the charges are moving at a constant speed Vy. So that contributes a current basically rho times Vy. Here rho is actually defined as a number of electrons per unit cell. So one need to divide by omega to get the electron density. So the other contribution of the Hall current is given by the electric field and the Hall coefficient sigma xy. basically the electrons in the moving frame fills this electric field, and this contributes another Hawk current. So the sum of the two currents actually give you the total current, which is basically this number. And this number actually also further turns into this number in the bracket. Basically this current would give you a Lorentz force. Basically the current across this magnetic field is the force operator. So the force, it turns out that the force is proportional to the velocity Vy times Eb, and with this vector here. And this vector, according to the Diophantine equation or the strata formula, is exactly this S nu, and this actually proves why it's basically a quantized response. Okay, yeah, let me now move to the part 2. So yeah, this is a kind of a different topic, but also there's some relation also to the momentum space dual picture I just mentioned, as I'll mention for two-spotted graphene case. Okay, so so the Hofstadter, one interesting property for the Hofstadter butterfly is actually if you examine a trio Hofstadter butterfly of trio bands, you find basically the spectrum are roughly bounded within the energy range of each band, at zero magnetic field. However, if you look at the Hofstadter butterfly of topological band, for example, this is an example of the Chern insulator with 2 Chern bands, you would find that the Hofstadter spectrum are connected between the 2 bands. Basically, the energy spectrum are no longer bounded within the range of each band. So this is kind of pretty general for many topological single particle models. And actually, we show that this is actually because of the absence of local linear functions in such topological models. So a rough understanding for such a difference between the Hofstadter spectrum of trio and topological bands are just based on the non-local linear functions. So basically, assume we just consider a lower band, the lower band, which is a trivial in this example, and topological in this example, in the Chern number example. So if we try to write down just a one-band model for this topological band, for trio band, there's no problem. We can just write down a model with short-range hoppings, because we have local linear functions in this case. But for a topological band, this hopping would have to be infinite range or long range because of the non-local nature of the linear functions of the topological bands. So when you create a magnetic field B into the system, these hoppings would acquire some phases in the model. So for trio bands basically one could prove that the spectrum of the system is always bounded by the norm of the sum of these hoppings, and actually this vector, one could see that this vector of magnetic field induced by magnetic field only changes the phase of T, but not changing the norm of T. So basically this tells us for trio band, the energy spectrum is always bounded by this number, which is actually finite because one has a short range hopping in this trivial case. But for topological bands, actually one has infinite range of hoppings, and this upper bound actually diverges. And of course, this is not proof that the spectrum has to be unbounded, but at least this gives you some sense that the spectrum, you would expect the spectrum to be not that bounded. And until the band spectrum would merge with other bands, which trivialize the topology, then one could apply the trivial argument here for the 2 bands together. So in the example of Chern insulator,
I have a question.
Yeah.
So when you say topological band, are you referring to Chern bands?
Here I'm just giving an example of Chern bands, but actually you could also consider symmetry protected other strong topology bands as long as they give non-local linear functions.
So in the case of, even in the extreme case of Chern bands, your linear function would have power law decay.
Yeah, yeah, would have parallel decay. So the sum of this T would diverge if you just do the summation.
But okay, if it has parallel decay, I guess I don't understand why the hopping would be infinite range. Why isn't it not parallel?
Yeah. So here I'm just saying in the rough sense, yeah, indeed it's parallel decay instead of infinite range. So yeah, I should say, yeah, thank you for the comment. I should say this infinite range includes the case of parallel decay. Basically, the definition is when this summation of the odd hoppings diverges. That's what how I define infinite range.
Okay, that's fine. But now you make the further comment that it applies to non-Chern bands which have some symmetry protected topology. But
Yeah.
for those cases, the one functions are they can be exponentially localized. They just don't respect some symmetry property.
Yeah. So actually, it depends on what symmetry imposed onto them. So some symmetries cannot do this. For example, time reversal symmetry would not do this. Actually, it's actually broken by the magnetic field B. But yeah. So actually, the proof is not by this method. This is just an argument. It can be shown that there are certain kind of real space invariants which give you the protection, but not for all kinds of symmetries, but just for certain kind of symmetries. I'll mention this again in the end.
Okay, thanks.
Okay, thanks. Okay, for the Chinese sorted case, actually, conclusion is more specific. That if you consider, for example, a two-band model with a Chern number C gap, you would find the gap actually closes at the flux per unit cell 1/C. For example, these two examples are the tie binding models with Chern numbers 1 and 2 respectively, and one could see that the Hofstadter spectrum of the two bands closes gap at 1 flux per unit cell in this case and 1/2 in this case, which connects the Hofstadter spectrum of the two bands. So there's actually a very simple proof based on the strata formula. Just consider this two-band model. The electron number per unit cell inside this Chern gap is given by the strata formula to be 1 plus this Chern number C times the flux per unit cell. So as one can easily see that at the flux 1/C, this number of electrons per unit cell would reach either 2 or 0, depending on the sign of C. So if one further increase suppose the gap is not closing, and one further increase the magnetic field, one would obtain electron number which is either negative or bigger than 2, which actually doesn't make sense. So this actually guarantees that the gap has to be closed at or before this flux 1/C. Okay, so actually this is a
May I ask a question?
Yeah, sure.
Okay. If the gap close at 1/C times by 0, does that mean this gap have a non-trivial Chern number?
Yeah, but so the converse statement is not necessarily true, I would say, because sometimes you could just overlap two bands and get a trivial band gap closing, but those closings are not protected. That's what I could say. I mean, if you observe a gap is closing, and that doesn't necessarily mean it's a topological gap, but yeah. But if you're allowed to vary the parameters of the system, those trivial closing would not be protected.
Okay, thank you.
Okay, thanks.
So
yeah.
So here you're talking about a two-band model, right? But it seems like the argument you gave before didn't depend on having a two-band model. Is that right?
Yeah. Actually, you can see here, as long as the other bands are far away, I mean, another thing could happen is that this higher band actually merges with a third band here before this gap closes. Then the situation could be a little bit different. But if the above trivial gap remains large, then this argument actually applies, right? Yeah, basically, I mean, if there is another topological gap above it, and this band could merge with the other band and changing the topological nature of this higher band, then this gap could, yeah, I would say could possibly extend to higher bands. Does that answer your question?
Okay, thanks.
Okay, thanks.
I have a quick question also. So
Yeah.
when you say it closes at or before, does it in fact always close at in all the numerical simulations?
Yeah, actually it always closes at, I mean, you could deform this spectrum, for example, it closes earlier, but those crossings would always be trivial. So you could, yeah, basically the only the closing at this flux is protected.
Okay.
Okay. Okay. Thanks. Yeah. So experimentally, this has recently been observed in the example in the system of twist double bilayer graphene, where one could actually realize Chern bands of Chern number ±2 under a displacement field E. The nice thing about this twisted system is that the unit cell, the effective unit cell, is actually pretty large, and one could create. So one could apply a magnetic field which is equivalent to unit number of close to 1 flux per unit cell in the Moire system. So this is the spectrum, Hofstadter spectrum of the lowest 2 bands. Basically, they are Chern bands, and so theoretically, numerical calculation indeed show they close at 1/2 flux per unit cell, and experimentally they could fit the gap by the transport, fitting the transport coefficient using the Arrhenius plot, and indeed one sees that the gap of all these different all these different electron displacement field actually tends to close at this 1/2 flux per unit cell with some errors of the fitting. Okay, so yeah, another example I want to mention is the twist bilayer graphene, which actually has a fragile topology, as many people has studied, including us. So yeah, I will not explain in details what this topology is, but just to mention that in the twist bilayer graphene case, the lowest 2 bands of the system at 1 valley has a non-trivial Wilson loop winding number. So this is basically the fragile topological index of the system. And actually, this topology, we actually showed it's actually stable if we notice that the twist bilayer graphene actually also has a particle-hole symmetry. And this is the Hofstadter butterfly. If you calculate the spectrum all the way up to infinite flux, in this example, one could see that the green parts are the spectrum of the lowest 2 bands, and it's indeed connected with the higher bands at 1 flux per unit cell. Basically, this is protected by the by the symmetry, by the topology of the lowest 2 bands. Yeah, as a result, if you look at the Landau fan diagram, basically the transport measurement, you see these Landau level gaps, which emerges from the Chern neutrality, actually extends to higher bands all the way, which is actually on Euro. For trio bands, these Landau levels emerging from this band would not extend to the higher bands. Yeah, actually, if you look at the different angles, there are actually some different cases in this spectrum that I would like to mention. Actually, there is a regime in the angle and lattice relaxation space where the spectrum of the higher bands and the lowest band are connected at infinite flux. Yeah, so one might wonder why infinite flux also counts in this plot. So this is basically because in the twist bilayer graphene model, when it's actually a continuous model and one does not have a period of the Hofstadter butterfly, but one could identify if one include the infinite flux into the Hofstadter spectrum, one could identify it as a part of the Hofstadter spectrum. So in this sense, the spectrum is actually connected at infinity in this case. And this actually can be the connection of the higher bands and lower bands can be proved by noting that at infinite flux, the twist-bilayer graphene model actually reduces to a monolayer graphene model in a momentum space. The only difference is that in that case, one should regard phi naught over phi as the effective magnetic field B. But due to time limit, I will not mention too much details about this proof. Okay, so this is just to show that in tight binding models of the fragile topology, actually, we also see the connections between different bands. When these two bands are topological, basically their spectrum are connected to the higher bands. And this is the model, the 10-band tight binding model for twist-bilayer graphene. And we also see that the lowest two bands are connected with the higher bands. So in general, the Hofstadter butterfly connection are protected by certain invariants called the real space invariants. But they actually generically requires, for this specific case of C2ZT protected case, they require C2ZT plus some other crystal symmetry or certain discrete symmetry that give you some real space invariant invariants. If you just have the C2ZT symmetry alone, actually it's strictly not protected as shown in this paper. Okay, lastly, I just want to mention that this is also observed recently in smaller angle twist-bilayer graphene. The reason to go to smaller angle is because there's an upper limit for magnetic field, and to see the effect, one really need to enlarge the unit cell. But in this case, actually, there are 8 low energy bands connected with each other. But actually, they're still topological given the particle hole and C2ZT symmetries. And indeed, we see the Landau fans. This is done by Dmitry Avtov's group. That the spectrum, the Landau levels from the lowest two bands actually always extend all the way to all the higher bands, which indicates a connection of the Hofstadter butterfly. Okay, I think I'm probably right at the time, and so I just conclude my talk, and I want to thank all my collaborators, and questions are welcome.